Hi everyone, good morning or afternoon, depending on where you are. I'd like to welcome you to GridIron's Accelerate Big Data Oracle and Oracle-RAC webinar. Thank you for taking the time to join us today. Just a few housekeeping items. This webinar is 30 minutes long and includes a Q&A session. You can submit all questions towards the end via the chat function. All questions will be answered. If we run out of time, send your questions to info@gridironsystems.com. Your presenter today will be Steve Phillips, and I'll turn it over to Steve. Steve?
Thanks, Rory. Welcome, everyone. Thanks for spending some time with us this morning. The goal of today's presentation is to give you a very brief overview of our technology, our positioning in the marketplace, and where we've had successes. By no means is this a technical deep dive. We'll have some technical content, but if you'd like to get some more information from the technical side, I'm the corporate SE here at GridIron. You can contact me directly, or you can contact your local representative. We can help you find that person. Sales@gridironsystems.com is a good way to reach out to us. So with that, let's get started. So as most of you may know, database usage is becoming very, very complex. The database sizes that we're seeing from our customer spaces are doubling every 18 months, kind of like Moore's Law. The working sets are getting much, much bigger. They're getting much more complicated, and they're exploding really and accelerating in the size that people have to do work and or analysis on. They also are requiring a lot of temp space for functions like joins, very complicated queries, temp spaces for other types of functions, and those are getting more and more necessary as time goes on. The usage model is also changing quite a bit. We're seeing a lot more ETLs. In fact, what we call a trickle ETL. In other words, you may see this in your environments where you're constantly moving data into a website or a web database, web-facing database, for customers to take a look at data, and the time where that data is important is becoming shorter and shorter. So in other words, you've got to refresh that data a lot. And that puts a lot of stress on storage devices and servers, but especially the I/O train, if you will. Those workload patterns are changing constantly. Time of day tends to vary, but also what we've also seen is with a lot of global companies, those variabilities tend to smooth out because they're servicing large groups of data in either APAC, North America, or Europe, and because those are spread apart by almost 8 hours, there seems to be a constant use of that data. So there's really no downtime for data. We also see that the amount of users that are accessing data is also exploding, especially with technologies like RAC, because you're able to scale those out linearly or partially linearly, and you see thousands and thousands of concurrent accesses, and that's another big problem for I/O bottlenecks. That's part of the reason why we're in business, and we'll get to that in a few minutes. But there's also quite a bit of dependency on things like latency, and that's really what we address. The storage arrays that are out there today, although they're very good at storing data, are not necessarily built to meet the data access requirements of these new databases and new types of usage for databases and the amount of concurrency that we see. So a lot of the functions like probing, temp spaces, and so forth require very low latency to be able to keep up to these new demands. And so what we'll do is we'll talk about some of the ways that we can address those. So when you do a lot of different things with a storage array, you tend to cause a lot of contention with that array and thereby really reducing the performance that you see across the board. So on the left-hand side there, you can see there's a whole lot of different things that you may have accessing a particular storage device. But the problem is a lot of those workloads are not only highly concurrent, but they're also very different. Some of them could be scanning in nature, some of them could be doing a lot of probed reads, some of them can be doing joins. A lot of different things could be happening all at the same time. And storage arrays, the way they're built today, are not really built to handle that well. And so what you see is, as you get to this concept of big data, where you have a lot of different accesses and a lot of different users trying to hit the same data set, you start to see a knee in the curve, if you will, and you hit a wall, where the storage array can only serve up so much data to those servers, and no matter how many servers you have and how much horsepower you have, your bottleneck becomes your I/O very, very quickly, and we've seen that with many, many customers that we've engaged with. So the solution that we've come up with is to put a tier in the fabric to lift some of the important data, and I'll get into what we call important, into the fabric layer. In other words, lift it out of the primary storage device. Now, there's a couple of very important benefits to doing that. Number one is you're lifting the read access layer into the fabric away from the array, and again, away from the controller. The controller is typically what causes most of the problems with a storage array. It's very, very good at storing data. It's very good at doing data management functions. But because it's relying on what amounts to a general purpose processor and software to manage that data, it's not really designed to service data at the kind of data rates that servers can access. So I'll give you an example. If you have a query that you're running and you want to run that query at 5 milliseconds latency, you can probably do that with an array that you have out there today, even if it's moderately busy. However, if you have an application that can take advantage of latencies that are far lower than that, let's say 200 microseconds down to even 50 microseconds, a typical array that's out there in the marketplace today is not going to be able to service the data at that kind of latency rate. And that's really where we come in. So because we don't rely on general purpose CPUs and software, we're a completely silicon hardware-based solution, we can service up the latency sensitive pieces of the data very, very quickly, in fact, down to the 50 to 70 microsecond range. The way we do that is through a feedback loop. What we do is we watch the traffic, as you can see here on the diagram, flow through our fiber channel proxy, and what we do is we take a measurement of how long that data took from the back-end array in order to be serviced. And then we keep that data in mind, so we have a baseline, if you will, for that data access point. And we do this for every block of data on the back-end storage that you provide to us through this proxy path. Then we watch that data and we say, the next time we service that data up, we're going to increase the responsiveness of that request by up to 100x. So let's say the next time this comes through, you're used to seeing that data at 5 milliseconds. Now we're going to service that same set of data at 50 microseconds. Now this is where the magic comes in. So we use our custom silicon to figure out, based on actual empirical data, whether or not the server reacted favorably to having that data serviced quicker. In other words, if the server reacted well, that would mean that it would either go get more data quicker, and we can measure the delay in between accesses for that particular server. And because we watch all of the data and keep a historical record of how that data is accessed, we can make a really good approximation of how much we've serviced that data quicker than the back-end array. For example, the access did not change based on us decreasing the latency up to 100x. We'll typically leave that data on the back end because there's really no value in caching or tiering that data outside the storage if we're not providing a positive effect for the application. However, in many cases, there are certain data sets, for example, indexes, some temp spaces, some tables that get very hard hit, there's a lot of concurrent access to, where we can service that data at a very low latency, and it does cause a very positive effect to the application itself. This is what makes our product very unique. Other technologies in the marketplace will typically only cache the data that is most recently used or most frequently used. We actually proxy and tier the data that is the most interesting or the most important to the server performance. The way we do that is we zone into the switch. It's a very simple process. It takes about 30 to 40 minutes. We script it all ahead of time to make sure that it's very clean. And we can get this thing in a matter of an afternoon. And you're immediately seeing the impact in a transparent fashion of your data set. So what we can do here is highlight to you what this means in terms of latencies when you compare it to a typical storage array. So even if you're doing tiering within an array, and you put in a whole bunch of SSD into that array, the bottleneck here is not necessarily the devices themselves, the SSD devices, it's more the controller. The controller has a limitation where you're not really going to be able to get data at less than 1 millisecond latency out of that array. We completely break that barrier, and we move that needle, if you will, to the left, and we're servicing data at between 20 and 200 microseconds typically from our combination of flash and RAM built on a silicon foundation. So what that provides to you is much higher concurrent I/O bandwidth for the vast majority of your applications. It's going to provide much higher IOPS, assuming that the servers have the headroom to get those IOPS, and provide you a much lower latency access layer to the data. We do this in real time. We can recognize patterns in your data. So for example, if we see that there's a certain range of data that is write once, read once, and then never read again, we can actually leave that in memory and then eject it very quickly. And we can recognize patterns of data to optimize our resources to do the best job for the application. And again, we do this all in real time. So the result of all of this is that your applications are going to run typically between 2 and 10x faster. Your read latencies are going to be either an order of magnitude or up to 2 orders of magnitude less. And you're going to be able to implement a flash solution in a much more elegant and common sense way than just putting it in an array and hoping things get better. Here's some examples of some proof points in different industries. I'll highlight a couple of them. The first one, Shopzilla, was particularly interesting. They had an Oracle data warehouse, and they had a trickle ETL, as I mentioned earlier. They wanted to keep that data up to date to their users. They're a web-facing company. They think like BizRate is one of their properties. And they would try to scan that data from literally hundreds of different clients across an entire 40-terabyte database, looking for patterns and looking for changes. These real-time reports typically took about 6 hours to run, and even though they had 4 very high-end frames on the back end, they were only able to get about 2 gigabytes a second in sustained bandwidth when they went anywhere over 20 users. users. We stuck ourselves in front, integrated with ASM, and we were able to take their reports down from 6 hours to nearly real time in their nomenclature, which is about a 30-minute delay. They figured that just from the storage and server consolidation point of view and Oracle licensing point of view, because they were able to redeploy some of their servers, they saved about $2 million pretty much right off the bat. Another example is Regulus. They had a number of different applications sharing a very high-end IBM array, and their Sun M5000 was running at about 100% CPU, and most of that was I/O wait. It was actually waiting for requests to come back from their high-end IBM storage array with an SVC in front of it. We actually reduced their CPU utilization on that server to about 45%, and their application ran about 3x faster. So they were able to, in a sense, get 55% of their server back just by putting us in place, and they could then add additional instances of Oracle without having to buy any additional licensing. So just on that alone, it was like getting a new M5000 for free with an Oracle license. So that saved them about $500K right off the bat. And then when you add in the fact that you're able to keep their storage alive a little bit longer than they expected, they save somewhere in the order of $1 million. And we've got many different examples of this. These are just 5. So I talked about Shopzilla a little bit. Here's a little bit more detail on it. If you look in the lower right-hand corner, that is an example of what our box will show you. Since we sit on the wire in the fabric itself, we can tell you exactly what's going on in the conversations between the initiator and the target, in other words, the server and the storage array. And you can see there we can take a baseline, which are the gray dots in the upper left of the chart. And you can see there they were not getting any more than about 200 IOPS, and those requests were coming through at about 200 millisecond latency. That array was really hammered. When we put ourselves in place and integrated with ASM, which took about a day to do, we were giving them on the order of about 2,000 IOPS on average. The latency was low across the board. It was less than 5 milliseconds, and we got them about 10 gigabytes per second of sustained bandwidth. Since then, they've gone up to about 12, and we got their CPU utilization down by about half. So at the end of the day, what they told us was that no matter how many concurrent accesses they had running, they had a very consistent quality of service for all of their applications and all of their users. They originally did not allow anyone to run ad hoc queries during the day, and they then allowed people to do that because they knew that it would not kill production if they had people running queries all the time. The other benefit is they had 5 Oracle-RAC servers in this environment, and they found they could do the same amount of work, if not more, with us involved with only 3. So they were able to then repurpose those other 2 servers for other applications, which obviously can be a huge savings in licensing. So here's the second order effect, which is also very interesting. What happens when you put us in front of an array is the array is going to see its access patterns get much different than if it was servicing all of their requests from a host. So because we were servicing the reads within the fabric, this is an actual chart from XIV. You may recognize this chart. And what we saw was as soon as we turned on Boost, within about 10 minutes, we learned enough of the patterns where we were servicing about 90% of all of the IOPS that were coming from the host. So you can see there were about 5,000 IOPS before we turned on Boost, and then within about 10 to 20 minutes afterwards, it was only seeing about 1,000 IOPS at the array. So we cut that by about 80%. Now, the other thing that's interesting here is the measure of how busy an array is and how overwhelmed it is latency. And it was servicing those requests at about 50 milliseconds before we were integrated and Boost was turned on. After we got in there, as you can see there, the chart really plummets. The blue line goes down under 10 milliseconds. So the request that it was getting, it was able to service much more efficiently than it ever was before. So the first order effect is the servers are going to get the data that is most important very, very quickly. The second order effect is the array is going to be quieted to the point where you can now do other types of functions that the array was too busy to do before. So, for example, things like data management, snapshotting, replication, things of that nature. This array was not able to do that because it was getting hammered by the actual application. Now, because we're servicing a lot of those reads from the fabric layer, this guy is able to do its work a lot more efficiently. So this box comes in 2 flavors. The first is a GT1100, which comes in a 2.5 terabyte model. The second is a GT1100A, which comes in a 6.5 terabyte model. And you can think of these as Lego bricks. So if you're scaling your application based on bandwidth, or IOPS, or capacity, we can scale linearly in all 3 directions. Down there below, we also give some ideas of how much data that can service. The ratio of the important data, or the data that's latency sensitive, will vary based on the type of applications you're running on it. VMware, for example, is much different from OLTP, and we can work with you individually to figure out what those ratios would be in your case. So what we found is that most users tend to start this in one area, and then they start to spread it to other areas of their organization. So where you may start with an Oracle-RAC implementation, you'll find that the headroom on these boxes is such that you're not using the entire 6.5 terabytes right off the bat, because not all of that data in your data set, even if it's much larger than 6.5 terabytes, is going to be latency sensitive. So what people start doing is they start moving other applications to it, like VMware, some smaller databases, etc., to start filling in that headroom on the investment that you've made with us. So this becomes much more of an infrastructure play that can help beyond just Oracle. We have a ton of success with VMware, for example, and we give very consistent, sustained performance gains for really any application across the board that's latency sensitive. There's a couple of different options out there in the marketplace. One of them is to use Flash in the server, and we've had a lot of questions about that. The downside to using Flash in a server is that it's only available for a single server. And if you want to use things like vMotion or Oracle-RAC, it's very difficult to take advantage of resources that are plumbed into a server. And in addition, if anything goes wrong, you've got to crack open that server to go get it. The benefit to using a proxy device that's actually sitting in the SAN is you can leverage that investment across not only a whole bunch of servers, but across a whole bunch of different storage arrays as well. So no matter what your environment looks like, having the investment sit at the SAN layer means the traffic conglomeration point for all of that information, and we can then take advantage of that position to accelerate applications across a wide range of servers and storage. So we feel this is the best way to go. You can put SSD in a controller, but again, you've got the same bottlenecks you had before, where a controller just can't keep up with a device like an SSD, and you've still got the same bottlenecks with data access you had before. So again, we can go into more detail with this if you'd like at a future date. From the ground up, we've also built in a full-blown enterprise-class management system. So it'll manage firmware updates. It keeps records of all of the data that flows through us for trending analysis and for data mining. So you can see exactly what the difference is between what you had before and what you have now in terms of performance, in terms of IOPS, latency, throughput, whatever you want to look for. We also have a very mature set of tools to go in and do these installations. We treat even when we're installing in dev and test, we treat it like it's production. So we have a full process where we go in and do an audit and gather as much information as we can to completely script and plan out the installation. That's why they go as smoothly as they do and as quickly as they do. So we're not talking about a 2 or 3 week or even 3 month implementation. We're talking about a 4 to 5 hour implementation overall. So it's very simple to get integrated. So typically the next steps after we talk to folks is they ask, how can we get a proof of concept going? So again, typically it takes about an afternoon. It takes about a week of planning or so forth on our side to get everything lined up. But for the most part, once we go in and prove our value of this product, they typically don't come out. The stickiness value is very, very high because people see the ROI very quickly when they talk about spending dollars for accelerated storage devices. What they found is by putting it in the network, they're able to leverage it, as I mentioned earlier, across a wide variety of applications, servers, and storage. And it really makes a lot of sense. And so we've had great success with that. That does it for the presentation. So why don't I hand it over to Rory, and he may have a couple of questions that came in from the audience.
Thanks, Steve. All questions can be submitted via chat, and you can, at the top of your screen, you should be able to have a little tab there that can activate your chat function. We do have a question that came in already, which is, how long does it take to evaluate your solution? And this is kind of 2 parts. What do we need to do to prepare for an installation? Is there any downtime involved?
Oh, that's a great question. So typically to evaluate the solution, it'll take less than a week. Typically what we need to do is see a single business cycle of the data come through, and we do some analysis on it. And then we turn on what's called boost mode, where we start allocating our resources to speed up the data access. And then typically within a couple of business cycles, we'll know exactly what that delta is. So a week is usually more than enough time to figure this out. So the entire project plan, including all the planning that's involved ahead of the installation, takes between 2 and 3 weeks. To prepare for the installation, we typically gather some very simple reports from the switch. There's not a whole lot of work that's done from the customer side. We actually do most of it. And then we develop a deployment plan that includes all of the steps we're going to be doing, all the scripts that we're going to run, and we review that with the customer before we do an installation. As far as downtime goes, for the most part, this goes in completely transparently. It does depend on the type of multipathing that you're using on your server, but typically if you're using any modern operating system, downtime is not required. There are a couple of exceptions, but for the most part, modern multipath software can figure out this change in pathing very transparently. It does not typically require downtime, especially not with RAC. Even if it did require a server reboot or something like that, which is pretty rare, you can always do one node at a time and do a rolling implementation. So typically there's no downtime involved. Rory, do you have other questions?
Yes, I do. This question came in. Our systems admins have had a lot of problems with some products where data corruption happens. Can you speak to the reliability of your product?
Absolutely. So typically these boxes, and I'll go back to the slide here, typically with most fiber channel products, they're sold in pairs for reliability reasons. So I'll take that question in two parts. The first is, what happens when one of these boxes fails? The second box will take over as both boxes are actually connected to both fabrics. So in the same sense that if you lost a switch, that's why you buy two switches for a SAN implementation, so the second switch will be able to carry the load. We do exactly the same thing. So being in the data path, that's very important. The other side of it is data corruption. So what we make sure that happens is, if we see a write come through our box, there's a couple things we do. Number one, we don't commit that write until we see the acknowledgement come back from the array. That's number one. So we can guarantee that our contents of our cache layer, or our tier, if you will, are always going to be consistent with the back-end storage array. So the storage array is always 100% authoritative. The other thing we do is we have these 10 gig links you see between the two boxes, and those are extremely low latency links. They're about 4 microsecond links. And they're actually plugged in directly to our chipsets. We did that on purpose. And the reason why we did that is to make sure that if we saw a write come in one path, before another read can come through another path and possibly get a stale answer, that data has been invalidated on the other side. So we've worked extensively with many of the storage vendors to make sure that no matter what they throw at us, there's no way they can corrupt the data. An Oracle is never going to get a stale or an incorrect answer in terms of the contents of a block. So that's a great question. Frankly, we probably wouldn't be in business if we corrupted data. So we've thought about that, and we worked very hard to make sure that can't happen.
The next question is there load balancing available?
So actually, that's a great question as well. So because the two boxes are sitting on the fabric and they both sit on both switches, they serve as an active-active pair. So no matter what box you go through, each box does have an independent engine in it, so you can get 100,000 IOPS out of each box. But if you're doing things like round-robin and ASM, where you're pushing data across multiple paths, you're going to see that benefit across both boxes. So it is an active-active pair, and you'll be able to spread out that load across both boxes and get the benefit of running them in parallel.
Okay, great. The next question is, did I hear that GridIron caches only reads? What do you do with writes?
I mentioned earlier just briefly that with a write, we store it in a holding area after we've invalidated both sides of the clustered pair. We sit it in a holding area, but we don't commit it until we see the acknowledgement come back from the array to make sure that we can be synchronized with the back end. And so with writes, what we'll do is make a decision based on the patterns that we've seen before in our algorithm, what to do with that data. So do we tier that data in RAM, do we tier it in flash, or do we leave it on the back end? We don't make any of those decisions until we're absolutely sure that that data has been committed to the back end. So in that case then, you may see the benefit of that data that's been written on the next read, or if we see that it's not latency sensitive, you'll see the same performance the next time you go and read that data because we're going to be getting it from the back end.
Okay, great. The next question is, we have Tier 1 databases that we would like to virtualize but are holding off due to performance problems from I/O bottlenecks. Can GridIron help in this situation?
Oh, that's a great question. We've got several customers. Gilead was actually one of them on one of the previous slides. That is their whole MO, if you will. They want to go and virtualize as many of their Tier 1 applications as they can. They picked off the low-hanging fruit, which is the first 80% of the app, your Active Directory servers, your small SQL servers, things like that. But where you run into problems is, if you try to virtualize a lot of these very high-end databases, you run into I/O problems very quickly. One of the benefits to virtualizing RAC in particular is that all of the inter-process communication in RAC, put it in a VMware server, for example, and we actually showed that at Oracle OpenWorld, where we had a 4-node Oracle-RAC running completely in VMware with a very low-end storage array servicing up a petabyte of data a day, what we were scanning through and doing full queries on. So because of that, we can actually make RAC more efficient, because instead of doing InfiniBand or 10 gig E between the nodes and having to go through the device stack of each of those nodes and then PCI buses and all that. It's actually done in shared memory within a VMware server. So the rack actually runs significantly more efficiently. The problem in the past has always been, how do I get the data in and out of those nodes or those virtual nodes? And we now take care of that access layer. So now these types of solutions are possible. In every VMware environment that we've been in, especially the ones that run databases, anywhere where we put our device in, it's never come back because the ROI is very obvious very quickly.
Great. Thank you, Steve. And that concludes today's webinar. If you do have more questions, please send them to info@gridironsystems.com. And I'd like to just announce one more time about what the next steps are, which is the next steps are to talk to one of our account executives. And to do that, you can just send us an email at sales@gridironsystems.com. And I thank you very much for attending our webinar.